All right, what's going on, everybody? Today we're going to be doing another LeetCode problem. This one's called sliding window maximum. We'll be doing it in C++. It's a hard. Let's get into it. So we're given an array of integers called nums, and there's a sliding window of size k, which is moving from the very left of the array to the very right. So we can only see the k numbers in the window, and then each time the sliding window moves right by one position, they want us to return the max the max within that sliding window. So for let's like input output. So for this example, we have this array and we have a window size 3 here. So k equals 3. They basically want us to just have a window of size 3 and at you just like moving it along the array at every possible position in the array where the window of size 3 could be. What is the maximum value at each point in order? So the answer here is going to be 3, 3, 5, 5, 6, 7, because I mean we could look at each window, but it's pretty straightforward. I mean 3 is the maximum of those three numbers, so we put 3 in the output array. Likewise for this one, and then all the way through. So yeah, I mean that's it for that input output. You can tell that for a brute force algorithm for this problem, it would be k times n minus k time complexity, because you're basically, and honestly it might even be worse than that. Well, actually no, it would be k times big O of k times n minus k, actually, for sure, because and I'll write it. So for the brute force, it would be this, because you would be searching for the biggest element in a window of size k, and then it would be n minus k, because that's how many different times we're gonna have to do that, pretty much, for how many possible positions that window could be in. But that's we can do better. So let's I'm going to zoom out a little bit here and basically just start with the code. So the optimal approach for this problem is going to be this is a sliding window problem, so we're going to use a sliding window, and then the trick really to solving this is to use a deck. And basically, there's an algorithm we can implement with the deck that'll give us linear time. It's going to be linear space too, because we're using a deck, but you gotta pick and choose those trade-offs for purposes. So so the time complexity is going to be big O of n with respect to the size of nums with the deck, and then the space is also going to be big O of n, because the deck is going to pretty much get filled up with every single element in nums at some point. So for the code, we're going to have, let's see, our output vector, right? So vector of integers, res, that's just going to be the maximum for each window position. And then we also have our deck. So in C++, we can declare that just simply like that. And basically what a deck is, if you don't know, it's just a data, it's kind of like a stack, but we can pop from the front and the back in constant time. So that's like very handy for this problem. Because really, technically, I think maybe you could just use a stack for this problem. Maybe not though, because either way, a deck is way better here, because we only need to consider, we're basically using it to remember, to save ourselves from having to go back and revisit numbers we've already seen, like in a previous window position. But what happens is numbers that you may have been considering before are no longer, this 3 is no longer going to be considered, even if you were considering it before. And we basically want to be able to pop elements from the bottom of the stack. So that's why the deck is useful here. We need to be able to manipulate both ends. So So we have that deck D. We're going to have our pointers. So in left equals 0, and then in right is also going to start at index 0. And I'm going to zoom in. I don't think we have that much code, so it doesn't need to be so zoomed out. So we're basically going to loop while our right pointer is less than the size of nums. So pretty typical. And then also incrementing our right pointer at the end as usual. Now the first thing we're going to do is basically see if our stack, see if the front of our stack, or the front of our deck, sorry, we're going to see if the front of our deck has a smaller value than the number that we're currently at. If that's the case, then we can get rid of that number in the deck, because we don't really care if we found a bigger value. Like that's the value we're going to want to use, right, in our current window. So that, I mean, that's pretty much the idea. So but first we need to check if the deck is empty, because if it is, we don't want to be accessing it at all, or accessing any elements in an empty deck. That doesn't make sense. So while the deck is not empty, and the let's see, it's going to be the value of the index. By the way, our deck is just storing indices, so we're going to have to reference into nums every time we want to get the value. So get a value of one of those elements. So nums d.front, this is just going to be the value of whatever element is at the front, or whatever index is at the front of the deck. And while that is less than the number we're currently at with our right pointer, we're just gonna pop that front element. So pop front, and then after that we can push the right pointer element to the front of the deck. So and again, it's just the index, so we can just push it like that. The next thing we want to do is basically check. So we want to make sure that our the bottom of our, whatever element at the bottom of our deck is still in bounds, like in our window, kind of like what I was explaining before. So like if our 3 gets eliminated and that's like still in the deck, we know we don't need to look at it anymore, so we can pop it from the deck. So the way we're going to check that is if we can say basically we want to check the bottom element of the deck. So if it's going to be we can use back to get the bottom element, and we want to just basically ask if that index is greater than our, or not greater, but less than our left pointer. And if it is, then we can pop that value. So pop back. So that's going to handle once we're no longer considering those values because they leave the window. And then finally, we need to have some code that basically updates the answer and moves the left pointer when it's time. So we know we can update our answer for our sliding window and start incrementing the left pointer once the right pointer basically gets past the window size. So to check that, we'll just say if right plus 1 is greater than or equal to k. So if that right pointer is has passed the window size, then we can add our answer to the result array, and the answer for this iteration is going to be, the way this algorithm works is it's literally just going to be the back of the deck. So whatever's at the back of the deck is going to be the max, because what we're using is pretty much called a monotonic decreasing. It's monotonic and decreasing, meaning all of the elements in our deck are always going to be decreasing. So what that means is basically the greatest element in our window is going to be at the back of the deck. So nevertheless, let's see, to push to our result array, we're just going to say res.push back And then again, it's the whatever's at the back of the deck. So it's going to be d dot, and they want the value. So no, we have to access nums like that. So nums, and then it's going to be d dot back. So that's going to add that to that max value to the result, and then we just need to increment our left pointer. And that's pretty much it for the code. Then we can return the result at the end of all this. Barring any mistakes, we should be good to go here. So let's run this. LeetCode's been a little bit slower recently, so bear with me here. I think they might be doing maintenance or something tonight. All right. Yeah, so again, this is going to be linear time and linear space. Linear time because we're just traversing the array with a sliding window. And every time we see an element, you know, there's just constant operations. And then this for space complexity, our deck is going to have at most nums elements. So linear space. So hopefully this video helped you understand the problem better. If it did, please leave a like and subscribe, and I'll see you guys in the next piece.